Yeah, we'll start the lecture in a couple of minutes. Okay, good evening. Welcome to this tutorial on principles of casting technology. Uh, this is regarding week 7, which is being covered in live session 6. So, my name is Rakesh. I am one of the TA for this course, and this is taught by Professor P.K. Jha from IIT Roorkee. So, in this week, there was discussion about melting and casting of cast metals and melting practice for grey cast iron, then marble cast iron, then SG iron, then followed by the casting of steels and alloys, and finally with the casting of non-ferrous metals and alloys. So before directly going into uh, the questions or assignment questions, I will just give an introduction, brief introduction to all of these lectures. Then I will, in between, I can visit some of the assignment questions and we can discuss. So in between, if you have any doubts, please let me know. So I will be using Professor slides as to discuss all these topics. I will discuss each and every topic in brief. Then we can have the questions. I hope everything is visible and my voice is clear. Okay. Okay. So the first lecture is about cast iron, different types of cast irons, and their melting, and what are the microstructures of it, and what is the significance of this graphite in this cast iron. So cast iron is like one of the material which is mainly used for damping purposes, and and it is the heaviest component that is being produced in this iron industry. And so it has cast iron has this damping property that was mainly used for making these machine beds. That was the main use of this cast iron, and it is highly compressive material, so it has good compressive properties. Then followed by the so we will discuss different types of cast irons available and what is the composition and gravitization in cast irons. So let me start with the before going to this what is the role of silicon. Let me discuss a bit about this cast iron. Okay. I hope everyone is familiar with this iron carbide diagram. So let me draw the diagram first. Just give me a minute. Just a minute. Yeah, actually, there was a problem with the document. It was such a time. Okay. So let me start with the phase diagram as I was discussing. So basically, so what I want to discuss is this cast iron is having this the carbon weight percent greater than 2. Okay. So if you see this carbon iron carbon diagram, percentage of carbon and temperature. Okay. So this is how a typical iron carbide diagram looks like. So I will write the temperatures as well. So we have around 1539 degrees Celsius. 7 degrees Celsius. Then this is 1539 degrees Celsius. Then this is 1135 degrees Celsius line, and this is 725 degrees lines. So anyone remembers what is this point? The red point. Okay. So this is the eutectic point, in which the and this is gamma arsenide, gamma plus liquid. So this eutectic line will get leadbrite, which is around 4.3%, and this is 2%, in which we'll get cast iron. then we have a tectoid point, which is around 0.8%. Okay. So these then we have cementite here, austenite here, then alpha ferrite, then we have perlite here. So these are the basic iron carbide diagram. So we are dealing cast iron is nothing but we are dealing after 2% of carbon. Okay. So I'll write the points. Tectoid. Tectic. So here this liquid is converting into two solids in this case. Then so now in this cast iron, since we are having this extra carbon, so we'll get a this graphite in terms of pure carbon. So that is the term we say graphitization. Okay, in which this excess carbon changes to graphite. So we have different types of cast irons, and the shape of this graphite is what changes the microstructure of each cast iron. Okay, and one more thing is, so we have this silicon which enhances this graphitization. So that is the reason we add this graphite uh, to enhance this graphitization. So this is graphite. This is graphite is a soft material, so we will get good amount of properties. Say this ductility or toughness will be increased because of this presence of this graphite. Okay. So now let me show you the diagram and discuss. Okay. So now just see this graphs. So just see this graph, left side graph and the right side graph. If you see on left side, so we have silicon percent on the x-axis and carbon percent on the y-axis. So if you see steels is nothing but below 2% and carbon is up to 2%, in which we are getting the steels. But above 2% of carbon we are in the white iron or white cast iron or malleable cast iron, which comes by heat treating of white cast iron we'll get, followed by the grey cast iron, which is having the highest carbon percentage as well as the highest silicon percentage, and in which we are also having this nodular cast iron. So just by the name itself, we can decide what is the shape of the graphite in that certain in the particular grey cast iron. And if you see on the right side, so we have percentage of silicon as well as percentage of carbon. So gray cast iron lies on the above, whereas the white cast iron lies below. Uh, so that it means the carbon percentage is more in gray cast iron when compared to the white cast iron. Okay. Suppose if this percentage of silicon is less, suppose in terms of steels, instead of forming this graphite, it forms perlite. That is the absence of the silicon percentage. Similarly, with the white cast iron also. So since the silicon percentage is less, so and also the carbon percentage is more or less less compared to gray cast iron, we so this graphite may be present in the form of cementite. Okay. So this is the effect of silicon on the different types of cast irons. So following up, I will discuss what is the cast iron, what is the microstructure that is being obtained with the different types of cast irons.
Sir, what is this dotted line?
This is for the, so this is the region in which this mottled cast iron is there.
No, sir, above there is some dotted line.
This one, right?
Yes, sir.
You see my cursor, right? So this is above which we are getting gray cast iron, below which we are getting white cast iron, and this is the region where we are getting this mottled cast iron. Understood? This dot below this dotted line.
Okay, okay, sir. Mottled cast iron means
Yeah. I will
steel
discuss.
cast
I will
iron.
discuss.
Okay, sir.
So I will discuss each and
Fine.
every cast iron. So now, so basically in gray cast iron, we are getting the shape of the graphite in terms of flakes, whereas in nodular cast iron, if you see, it is present in terms of nodules. So that in the microstructure part, I will be discussing in brief all these things. So now during solidification, so as I discussed, during solidification, we can get this graphite in different forms. So one thing is graphite completely, in which the silicon percentage as well as this carbon percentage are more, so that excess carbon can be converted in terms of graphite. We can also get this cementite in absence of this silicon as well. Cementite is the harder substance and harder phase, I can say, followed by the ferrite where there is less carbon as well as less silicon percentage, and same with the perlite and stearite is a eutectic compound of phosphorus and this carbon, and austenite is the unstable phase that is being formed below the 2% of carbon. So this is the different types of microstructure of this carbon presence in this iron. Okay. So this is one lecture, complete lecture. So now I will discuss these types of cast irons. So let me start with the first one, that is gray cast iron. So these are the slides of the professor itself. So the first one is solidification of ferrous carbon and silica alloy system. So as I discussed, silicon is the main alloying element in order to improve this graphitization process in cast irons. I will discuss why we need this graphitization to occur also. So it occurs in two stages: graphitization during solidification as well as in solid state. So one best example for this is this white cast iron. So basically in white cast iron, so this carbon, since the silicon percentage is less as well as the carbon also less, so uh, we cannot get graphite in terms of flakes, rather than it forms very hard substance such as cementite. So what we do, I will show that heat treatment process as well. So we heat treat it, this white cast iron, so that this carbon, this cemented breakdowns, and it forms carbon and iron, so that in that way it forms this graphite, so which is also called as tempered graphite. Okay. So then chemical composition effects. So one chemical composition is this silicon, and we can also, there are some other alloying elements as well, magnesium for example. So now let us see what is the effect of this silicon on the iron carpet diagram. So in the left side, if you see, we have different types of points. One point is where I can show my cursor, that is a eutectic point. See, it is forming at around 4.3 weight percentage. And if you see eutected point, it is forming around 0.8% carbon. Okay. So this is where we did not add any silicon in this. But if you add silicon on the right side, so this point of eutectic as well as eutected will shift leftwards. Okay, so that is one observation that was found by adding this silicon. So if you see silicon, if you see this eutectic point, it is between 3 and 4. It forms around some 3.6% of carbon, whereas without silicon we are getting 4.3% of carbon. Similarly, in eutectic point also it is forming well below the 1 point, around 0.5%, whereas in this case it is pointing around 0.8 percentage. Similarly, the other points also change effects due to the addition of this silicon. So this is the right side figure is addition of 2% of silicon. So this is the effect of silicon on iron carbide diagram. So according to this, we can define carbon equivalent in which, suppose if you are adding silicon, we don't need to add carbon to that extent. So I will discuss that formula once I discuss these slides. What is the carbon equivalent of this silicon and the carbon? So now let us see the different types of graphite flakes presence. So if you see the left top port is the kind of flaky substance. The right side is the type B is the crochet ungrouping. It's like a cluster formation, and the type C is like the dangerous flakes one, in which we are having these sharp corners. If you see, it has a sharp corners in which this is also kind of intermetallic that is used to form in non-ferrous alloys as well. So this is very brittle in nature, and this starts the crack initiation, and that is how the material fails well below its yield point. And then type D and type Z interdendritic segregation. So this segregation occurs since the solubility of this carbon will decrease from the liquid phase to solid phase, so it will segregate at the grain boundaries. So this is the different types of graphite structures that are being present in this gray cast iron. Okay. So each and every lecture deals with the different types of cast irons. For example, gray cast iron. Then next we can discuss about white cast iron, and then there is molding practice, and then there is foundry, and then inoculation is one thing, and the heat treatment. So these are the three basic properties that we have to be considered. So first part is regarding the microstructure and what is the chemical composition and how it is being affected on the cast iron. The second is the molding regarding the casting purpose. So here we are using green sand molding for casting these gray cast irons. Okay. And one of the reason for calling it as a gray cast iron is the fracture surface. So fracture surface looks like in gray type fracture, so we call it as a gray cast iron. Whereas in white cast iron, the fracture surface looks like white. So that is the reason we are calling it as a white cast iron. And now if you see, so basically we are for molding of this gray cast iron, we are using green sand, popularly used. And properties designed for this green sand is that it has a good shear strength, dry compression strength, permeability. So this is the permeability is the one of the important factor in order to avoid this gas porosity inside the castings. And since this mold should be heated to 1500 degrees Celsius, so there is a possibility of forming this fused material on the surface, which we cannot completely avoid but can be reduced. So which needs some other by adding this coal, coke, graphite, pitch, etc. in order to prevent these fused products. Or else we need to add another step to clean the cast before proceeding further sizes. So this is the different types of grain sizes of the sand that we are using for this type of molding the gray cast iron. So we should avoid the bigger grain sizes in order to avoid this penetration of metal defect. So the surface of the cast product will not be uniform. So that we need to take care. So foundry properties of gray cast iron. One is the fluidity characteristics. So one more thing is that addition of this silicon also promotes this fluidity in these gray cast irons. Okay. And we need to take care of shrinkage characteristics as well. So shrinkage characteristics in the sense, so if you have very bigger casting, so we need to provide the gate on the bigger casting rather than on the smaller castings. So because there is a chance of solidification in premature solidification before complete casting is filled. That is the one thing that we need to take care of shrinkage characteristics. some relationship between the gating design to the pouring rate, that prevention, and thermal gradient effects. These are the common things that we already discussed in molding. So one thing is the fluidity. So this is the it is the how ease we are we are able to fill the cavity. So that is measured by this. In which in the pouring cup we used to pour the metal, and we used to measure how much distance it has been traveled. So the fluidity can also be measured like this: 1.4 times the CF factor, which is nothing but percentage of carbon, silicon, and phosphorus. Okay, and T is the temperature. So that by this we can get how many inches this is being completed. So this fluidity can be increased by increasing the pouring temperature. And one more thing is the freezing range should be less for the fluidity, because if the freezing range is larger, so there is always chance of formation of solid combined with liquid, and it will restrict the passage. So that is one thing we need to take care. So if you are confusing with, I will show you one graph. Yeah. So if you see the freezing range is what I'm talking is this thing. So we have a line here. If you take some concentration, say 2% concentration, so the distance between the point intersection of point in this liquidus line to this eutectic line. So this is the freezing range we are having. So this range should be reduced if you are selecting different composition. So this range should be not only this gray cast iron. This fluidity is generally general item. So even in non-ferrous alloys, so that freezing rate should be less in order to promote this fluidity. And this is the one of the biggest confusion in gray cast iron. So because sometimes it can expand, sometimes it can shrink. So it all depends upon the type of graphite present in that particular cast iron. So solidification shrinkage is defined as 2 times percentage of graphitic carbon minus 2.8. This is the formula for the solidification shrinkage. And the volume shrinkage may be positive or may be negative. Suppose this percentage of graphitic carbon is more than 2. If it is less than 2.8, then we can get negative shrinkage. Suppose it is more than 2.8, we can get positive shrinkage. Positive shrinkage is nothing but uh, basically if you have a length of 100, so you can just provide 98. Sorry, you have to provide, if you want to get suppose in normal cases, if we have a string in 100 length, if you have a shrinkage of 2 so in order to compensate it, you will provide 1 or 2. Okay, so that finally it will fill 1 or 2 and it will shrink by 2 so it will come to 100. But in this case we have to it is a positive shrinkage. Basically it will expand. Okay, and then there is a no need for riser in this case because it is expanding. So basically, so we have to decide on this graphitic carbon percentage whether to keep the riser or not. Okay, so this is the concept. No risering is needed for the purpose of solidification shrinkage. So then comes the inoculation. So we have just discussed one is the molding, then this fluidity, then shrinkage characteristics, then we are discussing the inoculation, and finally we are discussing the heat treatment. So the inoculant is nothing but some substance which can nucleate
Sir, one question.
the primary phase. Yeah.
Sir, how do we know that graphitization process is complete?
Yeah, sorry.
How do
So
we,
that is,
what is the indicator that, how do we know that graphitization process is complete? Your last, yes, previous, yes, this one.
yeah, this one, right? So I have shown you this some micrographs, if you remember, right?
Yes, sir.
So we have to go by this metallurgical process, take the samples from the cast product. So
Yes.
once we then observe from the microscopes, get the percentage of graphitization that is formed with different types of process parameters. For example, pouring temperature, holding temperature, okay, in heat treatment process, and you get the result of how much graphite is forming, and you do the repeat the experiments number of times, get the statics, so you can get to know the parameters finally. So at this parameter, I can get this much of graphitization.
So by analyzing these structures, we can find the percentage of carbon.
Yes, 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 exactly.
Okay, sir. Is there any some notes available for this? How to calculate this about
Uh,
percentage of carbon from
so
this
this
type
is
of
nothing but,
microstructures?
yeah, it is very simple process. See, if you use some imaging process, this is very, yeah, we are having very good contrast in this type of figures. Even in the normal, this is just an simple image, but in actual microstructure also, you will have very good contrast. So if you simply apply some image processing tools, you can get the area fraction. For example, we have, you can see the tutorials online on ImageJ for finding the
What, sir?
area fraction. I will keep in the chat just a second.
Right. Okay.
So I have given you three terminologies. One is the area fraction, then the volume fraction, then using the tool name that is ImageJ. It's an open source tool. You can use easily. You can easily get the area fraction. So just watch the tutorials. You will get to know. So before processing, you need to do some basic operations on this segmentation. We call it as a segmentation in our terminology. So if you remember, if you take, so you have to do this for a good number of micrographs. Then only you can get the exact area fraction, which is also nothing but a volume fraction. The mean of area fraction, we can get a volume fraction in a given
Yes.
specimen size.
Okay, sir.
Uh, yeah, inoculation. So this is one of the interesting topic in which we we keep some particles inside the, for example, this titanium or vanadium particles or alloys in inside the caster and melt. So what happens is these titanium, these particles will go, and these serve as nucleation points, and these will enhance the grains. This will reduce the grain size, such as grain refiners, you can say, and they improve the mechanical properties, control of graphite structures, and elimination or reduction of iron carbide, or prevention of minimizing the undercooling rate. Okay, so this undercooling is very necessary factor in terms of power consumption. Okay, suppose if you have a melt which can melt before. Suppose if I have a pure aluminum which can melt around some 660 degrees Celsius, by just adding some, say, this titanium or vanadium, or just adding the silicon magnesium, I can just bring down that melting temperature to 600 or even 570, 580. So which can, so I now I have to give very less power when compared to the actual alloy. So that is how I can save uh, the energy consumption. So this will prevention or minimize the undercooling. So this inoculation, you can directly put in the ladle, or you can make them in terms of small tablets made of powder bonding inoculants, and you can just put in the melt. So typical inoculants we use is 72% silicon, 1% magnesium, 1% calcium, 2% aluminum, 4% ferrous. So these are the different types of inoculants that are used in this gray cast iron. some of the heat treatments. Uh, so you already know what are the types of heat treatment that are available. One is the annealing, then one is this normalizing, and then finally the quenching method. So we select the suitable heat treatment which improves machinability, suppose in terms of annealing, which also improves wear resistance in terms of quenching, strength as well as stress relief we can get in annealing. These are the benefits of heat treatment of this gray cast iron. Okay, and remember gray cast iron is nothing but we are having good number of cement carbon percentage, so it will it the hardness is well beyond the actual iron that we are known of. Okay. So let me discuss this slide as well. Then we can go to the assignment questions. So this is regarding ductile iron. So we just discussed gray cast iron, in which we observed that the graphite is present in terms of flakes. So now the problem with the flakes is it has the flakes has very sharp corners at the edges, so which serves as a crack initiation point as stress concentration, which can reduce the hinder the properties of this gray cast iron. So that is the why we use this ductile iron, in which we have this presence of graphite in terms of spheres. If you see, so it is in the form of spheres. Okay, so now we did not have we don't have that stress concentration. Okay, so the advantage of gray casting is it is also having low melting point, good fluidity, excellent machinability, and good wear resistance, which are also very similar to this cast iron. Okay, and it is comparable to steel, because advantage of steel also same: high strength, toughness, ductility, hot workability, and hardenability. Now why I'm comparing with the steel is, so steel it goes around some 1300 melting point, right? But cast iron is not like that. It can melt around some 1140 degrees Celsius. So same factor, the power consumption will be less if I go with the gray cast iron instead of the steel. Okay, now if you see ductile iron, this solidification at higher temperature as compared to gray iron. So we add this magnesium, cerium, and calcium or yttrium for causing these spheroids. So as I discussed, so we are getting this spheres, right? Sphere kind of iron presence, this graphite presence. So that is by adding this magnesium, cerium, calcium, and yttrium. And we also need this 0.05% of residual magnesium to achieve this spheroidization formation in most ductile irons.
Sir, these are used in the powder form or some other
Uh,
form?
so, so I have, as I discussed, we can directly mix in the ladle, or else uh, we can add in the powder form as well. Just before pouring into the mold, we'll just add the powder.
Yes, sir.
So the chemical equivalent for this formation of this spheroid is 4.3. So I will discuss what is this 4.3 indicates. As I discussed earlier, silicon is necessary for the formation of this, for improving this graphitization. And we can add this phosphorus, but we have to limit it to 0.05% only, because it affects the toughness. So this is the basic solidification of ductile iron. Then melting, basically we prefer this in cupola, because so since we need to add these things, these alloys, these things, magnesium, cerium, it is better we use cupola instead of so that we can put layer by layer and we can get directly, instead of using acid, because in acid melting is cheaper, but it doesn't remove the silicon sulfur presence. So basically we need to remove the sulfur so that we add magnesium in this. Uh, So I think there is method. Yeah. So let me discuss on this magnesium also. So basically, we add this sulfur is present even in this cupola also. Sulfur is present. So we reduce that. I think in the last class I have discussed. So in couple of furnace, so we add this magnesium in order to remove this sulfur presence in the pig iron as well. In this case, ductile iron. Okay. And if you see in hyperelectric gray iron, so basically this graphite whichever is present, it is of low density. It forms on the surface. It precipitate on the surface as carbon flakes, which is with this phenomena is called as kishing. Okay. And okay, let me discuss. So this magnesium is also usually alloyed with different elements in order to get the recovery. So I will discuss about this recovery in this method. So basically, this magnesium, whatever is we are adding to this ductile iron. So basically, we have to add it to remove the sulfur. But how we add this magnesium? Because magnesium is very volatile in nature. Once it get contact with the air, it burns violently. So that is the reason we actually follow some methods. So here they have provided three methods. One is the open ladle method, sandwich method, plunging method, and mechanical feeder. Okay. So initially, first the open ladle method. It is just by magnesium. So in a furnace, at the end we keep this magnesium alloy, and we just pour the metal on it. So when whichever the metal is coming in contact with magnesium, it will oxidize this sulfur and it will remove. It will form Mg magnesium sulfide and it removes that sulfur. So that is the open ladle method. The second one is sandwich method. So in this, what we do, we make a sandwich structure of steel plate, iron chips, ferrosilicon, along with this magnesium. So the molten metal will come first, melt the steel plate, then melt the iron chips, then melt the ferrosilicon, then it melts them. It will come in contact with magnesium and it will deoxidize. Uh, it will get deoxidized. That is the sandwich method. Then the plunging method. So basically, we will have a vertical. I will discuss this plunging method. We need a good explanation, pictorial explanation. I will discuss. Then the mechanical feeder. It is feeding this magnesium mechanically while pouring. Then we'll feed the magnesium along with it. Then this comes the inoculations. So here we are using ferrosilicon alloy as an inoculant in this case. So same as the gray cast iron, in ductile cast iron also we are using green and dry sand molds. So all the things will be similar. So we should not have a moisture content. It should be permeability should be good, and we need to pouring temperature will be 14 degrees Celsius. So this we need to remember. It will be, this pouring temperature will be around 1140 degrees Celsius. We need to add some a bit of superheat so that it will not solidify. So it is around some 1400 degrees Celsius. So that is where the pouring temperature of this cast irons lie. So basically, this magnesium addition will also increase the surface tension when compared with gray cast iron. So now if the surface tension is more, so this mold will not burn. Previously, we are having this effect of fused sand on the surface of the cast product. But in this case, we are having good surface tension, so the sand will not get come in contact with the this cast product because of this non-wetting characteristic of the sand. So this fusion will not be there in this case because of this magnesium addition. And the rest of the practices will be more or less similar. And then heat treatment. So similar heat treatments will have annealing, normalizing, hardening and tempering, and stress relief. Okay. Then we have this malleable cast iron. These are the types of iron with graphite in the form of irregularly shaped nodules. So malleable iron, it has irregularly shaped nodules. This is how it looks. So this is also what I was talking. So we have this graphite area and we have this grain boundaries area. So we can easily calculate what is the area of this graphite, and then if we just divide by the total area, we can get how much graphite is happening in this case. So basically, this malleable iron comes from the white cast iron. So basically, white cast iron is having unwanted properties, and it has very less graphite because of the less silicon percentage and carbon. If you remember the first diagram, you have less silicon as well as less carbon. So this graphite presence is less. So that is why we heat treat this white cast iron in order to get this malleable iron. I will show you in the further slide how the heat treatment process looks like. Yeah, this is the heat treatment process. So initially we transform this into perlite, into austenite. That is what happening in the 2 hours. Then we'll increase slowly and we'll soak there for 11 hours, followed by slow cooling and for again 19 hours. Then we can get this transformation is happening. So the steps is like initially nucleation of graphites, the steps in this whatever happening in this annealing process. So initially what happens is the graphite get nucleated. Second is elimination of massive carbides. These carbides will break down some Fe3, Fe2C, Fe2C and cementite into 2 times Fe plus carbon. So that is how it breaks down. Then the third step is slow cooling through allotropic transformation range, the formation of complete ferritic matrix, which is soft along with the graphitization. So that we'll get malleable cast iron, which is having good ductility and which is having good toughness. Okay. So let me discuss this plunging method for addition of magnesium, and let us solve some of the assignment questions before proceeding to the next lecture. So in this plunging method, so basically we will have a container and we'll put the magnesium here and we'll fill the mold, this mold completely. Then we'll tilt the mold. So what happens is, so that this molten metal will come in contact with the magnesium slowly. So finally we will completely tilt the stage, this mold. So this is known as plunging method of adding this magnesium to this ductile iron. Okay. So now let us solve some of the numericals. Sorry, now some of the theoretical questions. So the first question you can read. Yeah, I think I will explain. Yeah, just you can answer, then I will explain about this carbon equivalent using this phase diagrams. You can put the answer in chat box or you can directly unmute and speak.
Sir, I think B is the answer. Carbon plus silicon by 4.
Okay, we'll see. Okay. So actually, it is not by 4. It is like carbon plus silicon by 3. In some cases, phosphorus by 3. By 3 is the factor. So option A is the correct answer. So I will spend some time in this. So this carbon equivalent is nothing but carbon plus, in general, silicon by 3. Percentage of carbon, percentage of silicon by 3. Suppose if you are adding phosphorus also, then okay. So let me take a simple example of only silicon. So in generally, in eutectic point, so we are having this carbon equivalence of 4.3 percentage. If I am wrong, not wrong. Yeah, 4.3 percentage. Then silicon percentage is 2 percentage. Then actual percentage of carbon is this carbon equivalence minus this silicon by 3. That is silicon carbon equivalence we are having 4.3 percentage minus silicon percentage is 2 by 3. So 4.3 percentage minus 2 by 3 is 0.67. Okay. So 3.63 percentage of carbon. Okay. If you remember, I have shown you two different of iron carbide diagram, left and right. Right side I have added 2% of silicon. So all the points of this eutectic are shifted leftwards. So actually it should be 4.3%, but we are having 3.63% in the other figure in which we are adding the silicon percentage. This is how this addition of silicon affects the composition of these points. Okay. So answer one is the correct option. Let us see question number 2.
Sir, C.
Okay.
Yes, flakes having good damping capacity and good machinability and
Correct.
fluidity.
Correct. So this option 2 is the wrong answer. So correct option is C. So basically, as I discussed, this stress concentration will reduce the toughness, not the increase the toughness. So this is wrong. So C is the correct option. Okay. Yes.
Sir, I think C.
Okay. Let me read. So the following statements are correct. White cast iron is the starting material from which malleable cast iron is produced by annealing. This is the correct statement. The structure of white cast iron consists of massive carbide and pearlite. This is true. Like it consists of massive carbides and pearlites. That is also true. So this being the reason that silicon percentage is less in this, as well as carbon also less. So option C is the correct answer. Okay, let's move to the next question.
Sir, in first statement, it is written represented by the reaction. Which reaction, sir?
The pressure control. Okay, I think the reaction is not given. Okay.
Okay, sir. Sir, what is this metastable phase? I don't understand, sir.
So it is like a pseudo phase, kind of austenite, you can say. Similarly, iron carbide. So what is happening? It exists at higher temperature, but at lower temperature it is not stable, so it will form perlite or cementite. So that is one example of metastable phase. Similarly, in this case, the metastable phase is iron carbide, which is getting split into iron and carbon. So the phase is not stable at lower temperatures.
Sir, not clear, sir. No idea.
Okay, okay. So so generally phase is what. So we have one is stable phase. Then we have this metastable. Okay. So so in this figure, see this is austenite. Okay, which is a phase, but it is not. This is not stable. It is once you cross this 725 degrees Celsius, this austenite will not be present. It will be split into perlite or ferrite.
Means below
Okay.
725 degree it is perlite plus cementite.
Yes, yes. It forms. Actually, it's a perlite only. I'm just writing. I'll remove this one. Okay, it forms perlite. Okay. So this
Okay.
austenite basically what is happening? Uh, this phase is converting it. This austenite is converting into one perlite phase. Okay, I'm not sure about this, but what I want to say is this particular phase is not stable at below this 725 degrees, whatever.
Yes,
So
sir.
we call this phase as metastable phase.
Okay, sir.
Okay, understood?
Yes, sir.
Yeah. It is not a stable phase at all the temperatures.
Okay, sir. And sir, actually in the books it is alpha, beta, gamma, delta, iron.
Yes, yes.
Alpha, beta, gamma, and delta. Actually, this
Hmm.
iron diagram to remember it is sometimes difficult. Alpha, beta, gamma, then austenite, then
So these are like the phases they given. So this is alpha iron. This is gamma iron. So we have here delta.
sir, just this is alpha is below around 725 degree,
Yes, yes. This is the first
and where is a
alpha
beta?
phase. So beta, I think here we don't have beta. We have
Okay,
alpha, gamma, delta. Only these three.
alpha, gamma. Gamma is where, sir? Gamma means
It's
austenite,
yes, yes. Gamma means austenite.
and delta means, sir?
Delta means delta iron. That's it. Like we
Okay,
say alpha iron.
okay, sir. Fine, fine.
And here we have delta plus liquid. We have delta plus gamma. Here we have alpha plus gamma, and so on.
Okay, sir. Fine. So means less than 2% we are talking about the steels,
Yes, yes,
and above this we are talking about the cast iron,
correct.
and it is below 725 degree. Uh, so this is less than 2% we are getting perlite.
Correct, correct.
Okay, then it is moving towards the ferrite, you know, sir.
Okay.
After like 2% of carbon.
Mm-hmm. I will show you it. So basically, this is ferrite. We also call this alpha iron. Then we have this here. This is perlite, and this
Right.
is leadbrite. Okay. Now,
Right.
whatever present in between, so this region is ferrite plus perlite. So I have given P for this. I have given F for this. Okay.
Yes, sir.
Then we have here austenite plus cementite. So if you see different types of iron carbon diagrams, we can get what exactly which phase is present. I will show you one. I will send you. I will put the in chat. You can just have a look. So there it was clearly written everything. Just check this. I think most of the phases are written in this.
Right, sir.
I think we don't have perlite here. Instead we'll have cementite. We just see. It was clearly noted everything. You can just say. Okay. Let's move to that question.
मेरा ले बेटे दिन में ये तो जरूरी चल रहा है. So I think, sir, first statement is correct.
Okay.
Second, I don't understand. So second statement. Temper carbon means, sir.
It is just a kind of synonym.
Right, sir.
So basically, we are taking this white cast iron. We are doing some annealing treatment, and then we are getting this malleable, right? So in which we are breaking down this carbon, hard carbon, into graphite. So this also we call as temper carbon. Okay.
Okay, sir, fine.
This carbon. So in this case, both the statement will stand true because this is the how this this what is this metastable phase iron carbide is broken down into iron and carbon, and this is by this carbon is also called as temper carbon.
Right, sir.
So it will be like this temper carbon. Okay. Then yeah, we'll draw all the micro. So regarding the microstructures, we have a discussion. So let's move to the next question.
Yes. Sir, second statement is wrong,
Okay.
but I don't know exactly about the first statement, sir. Why fluidity of alloy steel is low as compared to cast iron? Yeah.
Okay, I think I will discuss the steel part. Then we can go to these questions. Okay.
Right, sir.
Let's briefly discuss the steel part. So this is regarding the steel part. So basically, steel is very famous for its high tensile strength and ductility combined. Okay, and these properties are controlled by varying this carbon percentage. So basically, we have different types of steels, like low carbon, high carbon, and medium carbon steels. And it will also show isotropic behavior, which is the behavior uh, which has the same properties in all the directions, known as isotropic, and is easiest for welding since the carbon percentage is less than 2%, and but it needs an extensive risering as well as high pouring temperatures. So steel is around some 1340 15, around 1500 above only, so it is very high temperature pouring things, and it
Yes,
will
sir.
go for extensive, and it will have shrinkage and everything, so we need good risering in that case. We'll discuss that in the molding part.
Hmm.
This is the molding part. So basically we can use dry sand, or we can use dried cement. Bonds sands are normally used. So basically this is not advised, the cement bondeds only advised if the moisture content is completely removed, or it will create a problem. Then we can use, but we cannot use permanent mold castings because they are meant for low melting points such as aluminum, zinc lead. So we cannot go for these permanent mold castings. Graphite molds can be used with precaution because there will be a pickup of carbon. Okay. And in green sand molding, care has to be taken for high values of refractiveness, durability, high permeability, and low moisture content. Okay, so this permeability is also same as I discussed. It should be very good, otherwise we'll get good amount of gas porosity.
Sir,
So we can have
here
investment. Yeah.
graphite means when we pour the molten metal, that can pick the carbon from it.
Huh. So this mold is made of graphite.
Yes, means it is
So
having the carbon contents.
yeah, it is pure carbon
Yes, sir.
graphite. So there is a chance of iron graphite picking from this graphite molds itself
Okay, so it is used with precaution,
with precaution. Yes.
means something is added or some additives, something like.
Uh, I am not quite sure, but it should be limited to limited number of castings. So initially, for first 3 4 castings, there will be no pickup. You can clearly see, but with the time, what happens? The graphite loses its bonding strength. Then you
Okay,
have to be really careful on using it or throwing it away.
right, sir.
Okay. Uh, so this can be in special casting. It can also be used in special casting such as investment casting, shell casting, or ceramic mold casting. Then, so coarse is well known. We can use coarse to get in hollow cavities. But there will be some defects such as hot tear. So hot tear is uh, it is nothing but, so basically the problem arises when the metal is cooling from the liquid zone to from liquid to solid. So uh, it will have some range. In steels we have this range, so that is nothing but semi-solid. There will be good amount of mushy zone present. So what happens is, while cooling, suppose if you have a good amount of structures, the the mold system, just assume a mold system, so such that while cooling, uh, there will be a certain region in which the strength of the mold completely less, because it is still in liquid stage, because the solidification can happen at any point. But if there is any certain area in which the molten metal is still in liquid stage, so we will have these shrinkage effects, or the complete mold can shrink. So if there is any region where it's still in liquid state, so there it can form these hot tears. Hot tears is nothing but we can get that crack shaped thing. So this also happen if you have unyielding supports. A simple example I can say, you can assume an I section. So if the top and bottom are cooling faster, so at the center we'll have very less time to get solidified. So there it will be still in liquid state. So it can clearly tear off. So that is called as hot tear. And metal penetration occurs if you have very coarse sand. So on the surface you can clearly see that metal is penetrated into this mold walls. And oxide formation. So oxide formation. Then coming to the solidification factors, one thing is fluidity, temperature level of solidification. It has a very good promotes progressive solidification because it has very good temperature gradients. So in the mold it will be like 1500, and the surroundings it will be around room temperature. So the delta T is very high. So you will get a progressive solidification.
Sir, the question is about fluidity, na? Fluidity of steels is better than the cast iron. Is it true?
Yeah, that I will discuss.
How can we see this? Okay, sir.
So fluidity. It affects on two properties. One is freezing range. So if I can say this, pure metal is having very good fluidity. Okay, and if the freezing range is more, this fluidity will reduce. We'll come to that. We'll come to that. Then this steel making can happen in different types of furnaces. One is open hearth furnace, electric arc, converter process, electric induction, or vacuum melting. So this acidic basic is nothing but the lining that we are producing. So if we are getting a slag which is of acidic kind, we need to provide a basic kind of lining, so there will be no reaction in that. Okay, so that is how this acidic basic lining is. Then we have this electric induction process. Then in which we'll get through the eddy currents, we will melt the steel, which is very good technique we can use, because here it will have a what formation of this. We'll have a mixture, electric induction mixing. We'll have in case of electric induction heating. We'll also have vacuum melting. So basically, we are melting inside a vacuum chamber so that there will be no interaction with the atmosphere, so that it will not form any oxides. Then immediately we will transfer it into the molds. So basically, before transferring molds, we can inject oxygen, or we can deoxidize, or we can produce heat treatment. Deoxidization is nothing but we induce hydrogen, so that it will react with the melt, and it will deoxidize it. But care to be taken, because hydrogen can also get absorbed into the melt, and it will form the hydrogen porosity. So casting of steels is like, we need to eliminate the shrinkage. All casting must be fed in heaviest section. I have explained this earlier. So if you have a thin section and a heavy section, first we have to feed the heavy section, then the thin section. Otherwise, the thin section can freeze, and uh, it will restrict the passage of the fluid into the heavier section. So no carbonaceous material or washes to be used in casting because of this high carbon picking. Use of new facing sand around the molding sand, so that we can get very good surface finish of the cast. So we have to deoxidize it by adding aluminum, magnesium, silicon. So this will form these slags that can be removed, and we should have ensure proper directional solidification. Otherwise, we'll get some defects such as hot tears. So of the gases in steel is oxygen, nitrogen, or hydrogen. Main is this hydrogen. Hydrogen is in aluminum as well. This oxygen induces temper brittleness and decreased resistance to corrosion, whereas when we use this chromium and titanium, even the severity is there. So this is the main factor with the hydrogen. So it forms these pinholes. So what happens is, while transferring from the liquid to solid, this solubility of hydrogen decreases, and it will try to go out of the mold. So it will, from the middle of the mold or from somewhere, it will go till the top and go away. So it will form a nice path. That is nothing but the pinholes.
Sir, this happens during solidification.
Yes, yes. This all happens during solidification.
Okay, when the temperature decreases, so this hydrogen means this is like it is exposed to the it wants to like come out of this है ना,
Yes, yes.
mold
From the inside the mold
casting.
to the top.
Okay, so pinholes generated due to this
Yes.
gas
Yes, yes.
exhaust.
Similarly, with the different type, means we have different types of effect with absorption of oxygen. For oxygen, we'll have a brittleness, and for pinholes, for hydrogen, we have a pinholes, which can serve as a stress concentrator and can crack easily. And with nitrogen, we have this stone-like fracture in steels, so it's something like brittleness. So that is the reason we use this vacuum melting or degassing in order to remove all this oxygen, nitrogen, and hydrogen. So here is that we have three different kinds of steel: plain, low carbon. So tell you the composition.
So I think plain carbon steel is up 2.3%, and
So
low
yeah,
carbon steel is 0.3 to 0.6% of carbon,
okay,
and high carbon steel is greater than zero point 0.6 up to 1.4.
yeah, yeah. In different books, different kinds, but in this plain carbon steels is like below 0.2%. Between zero point 0.2 to zero point 0.5, we have low carbon steels, and above zero point 0.5, we have high alloy steels.
Okay, but sir, if some objective type of question is there, then how
They
should
will
this?
give the range. So
Okay,
according to that, you have to select.
right, right.
Because we have very good, so plain carbon steels maybe zero point 0.2, as you said 0.3, but low alloy steels is will go between zero point 0.2 to zero point 0.5,
And this
and high.
plain carbon steel is also known as mild steel, sir. The
Uh,
carbon steel with 0% carbon is known as mild steel.
I cannot exactly say 0.2%, even less. Mild steel will have even less. So
Right,
basically, it will not react with. It doesn't have a heat treatment capacity. We cannot heat treat it. So that
right,
is the reason why we call it as a mild steel.
right.
Okay. So now coming to this fluidity, basically, let me share the screen.
So actually, there is nothing written. Only heading is fluidity.
Yeah, it is not written. Let me see. So basically, I covered it so that the other questions also get covered. But fluidity, I will discuss. Okay. So in coming back to the question, fluidity of alloy steel is low as compared to the cast iron. That is, first, the casting of alloy steels is relatively easier than casting iron.
Sir, casting of
Second,
cast iron is easy as compared to the steel,
yes, cast iron is relatively easy, right?
because I think in alloy steels we have to take a lot of like careful steps.
Mm-hmm.
But fluidity, sir, this is not actually. How can we compare fluidity of cast iron if some data is there?
Yes, yes, I will show
Either
it right
it
now.
is based on some temperature, sir, melting point. No, but how can?
So this is the wrong statement.
Yes, sir.
In several aspects, we can
So
talk
I
about
think
this.
yes, sir. First one is left now.
This is wrong. This is wrong. Only so we have to see about A and B. So let me discuss now. So for this, we have to go back to this iron carpet diagram only. Okay. So now if you see these steels, so this is the region we are dealing with the steels. So basically, what we have to keep in mind is the freezing range. This is the region for the steels, right? So freezing range is nothing but this is the freezing range. Liquid plus one solid plus liquid. You see, right? That freezing range. So this fluidity is inversely proportional to this freezing range and directly proportional to superheat. Right? If you heat more, then the viscosity will be very less. It can flow easily, and it will inversely proportional to the freezing range. If you have a large freezing range, what happens is, suppose if you have a path like this, if the liquid is flowing. So if you have a large feeding range, anywhere you can, this solid can form, right? and it will block this passage of this liquid. So the fluidity will not be good enough in this case. Suppose if you have a less fluidity range, what happens? This fluid can flow easily before the solid is actually forms, because it has a very good, suppose this is 1135 degrees, this is more or less close to 1300 for example. So we have a range of 13 degrees Celsius to 1135. So this is the range in which the solid can form. Suppose less freezing range in nothing but, suppose I have 1200 to 1135. Okay, this is the less freezing range. So which will be favorable, in which case the fluidity will be higher?
Bottom one, 1200 to 11.
Yes, exactly. Because it has a less chance of forming this solid while it forming, while it flowing into the mode. So that is the reason. Uh, that is one of the factor for fluidity as well. So you can just remember this: the fluidity is inversely proportional to this freezing range. Freezing range is nothing but this liquidus line to this solidus line. Now I'm just talking about 2%. You can take at any percent. So you can take it, say, 1% as well, and see how much is the freezing range as compared to the cast error. So this is the large freezing range, whereas this cast error. So if I start here, I have this much, but I I think I have drawn both at same level, but it will be a bit less. So this is the freezing range in case of cast error. Okay,
Yes,
and
sir.
we also have to remember. So we have to consider this point as well. Okay, this 1539, because there also we are getting this delta phase, right?
Mm.
So basically we have to consider from 1539 to this 1135. So that is the freezing range for these steels, because here also we have a chance of forming delta. Okay, so in order to clearly get an understanding, so basically, so this percentage of carbon, say I have say some 2%. So this will not be uniform everywhere, right? So at certain region I can get a concentration, say 0.8%, at which my delta phase is present. So suppose in this area I have 0.8%. So which is good enough, I can form a delta phase, right?
Yes.
Correct? If you understand this concept, it is easy to understand this freezing range. So we have several. I can explain one more thing regarding the same. So basically, this solid will have less solubility of carbon. Do you agree with this?
Yes, sir.
So basically, that is the reason. So initially, delta phase will form, and it will reject the this whatever carbon to the surrounding world. So initially the delta phase is the easiest phase to form, because it requires the less amount of oxygen, sorry, carbon. So what happens, this will reject the carbon into the phase, into the surrounding melt, so that the surrounding carbon percentage will get enhanced uh, minute after minute. So finally what happens, it will be too much carbon percentage. so that we can get this graphite formation also as well. So that is also one explanation I can give. So that is the reason we have a very good freezing range in steels, whereas I have drawn this at the same level, but we have less in cast iron. That would be the best explanation, good explanation. You can even search more. So that is the reason we have fluidity of alloy is low when compared with the cast iron. So finally, one formula you can blindly follow is this: whatever freezing range is directly proportional to the pouring temperature at the superheat and inversely proportional to the freezing range. Sorry, this is fluidity. Okay.
Yes, sir.
This. So option A will be the correct one.
Correct.
Let's see the next question.
सर थोड़ा जूम कर देंगे सर.
Huh?
सर जूम कर देंगे थोड़ा सा.
Fine. The first option is the presence of phosphorus lowers the melting point and improves the fluidity of the metal. The second point is sulfur is generally present as iron sulfide.
Sir, I think first point is correct. Like presence of phosphorus improves the fluidity.
Okay.
Second one is also correct, sir. Since sulfur is generally present in iron sulfide. Yes.
Yeah, this was not discussed, but generally it presents as iron sulfide.
No, sir, there was one point about sulfur. Na? Sulfur is added or it is something
No, no, no. It has to
creating
be
some problem.
reduced. It is not good for this iron. So we just add magnesium to it to
Right.
form magnesium sulfide, and it forms as a slag, and we can remove it.
But it is present, na, sir. That is true.
Yeah, very less amount of sulfur is present.
Yes, sir. I think both is correct. C option.
Yeah, option C is the correct. The presence of phosphorus lowers the melting point, so we have good fluidity of the metal. And second is generally sulfur is present as iron sulfide. If you are not adding magnesium, then it will be present as iron sulfide. So next question. This is about the eutectoid concentration.
Yes, sir. I think this is pointed is eutectoid steel, sir. B. Option B, sir.
Yeah, these are called eutectoid steels. This is the famous question.
Steels containing less. Sir, I think this is hypo B.
Yeah, they are called hypotektite scales, and above we call as hypertektite scales.
Above 0.8, it is called hyper.
Hyper, correct. Okay.
So both are correct. Option C.
Correct. Both are correct. So high refractive values of molding sand is used in case of steel due to high pouring temperature,
Yes, sir.
which is around.
And
Then
no
no carbonish
carbonate
metal should be
material.
used on the molecules in case of casting. It has tendency to dissolve in the molded metal, which is not good.
Sir, what is this
So
wash
both.
is actually? Carbonaceous material is okay. Wash is I don't understand, sir. Washes means
Material washes. It is just a terminology they gave. Just let me. I will check that.
no carbonate material washes.
Yeah,
Are
I
you
think.
sharing something, sir?
No, no, no. I'm not sure. I'm just seeing. I think. Okay, this is one of the name actually. So carbonate material also called as washes. There is missing
Okay.
R here. Okay.
Washes. Right.
These are just a terminology they use generally.
Okay, sir. Sir, option B, iron, carbon, nickel, and chromium.
Yeah. Chromium and nickel are the main elements, then followed by iron carbon. So B is the correct answer.
Yes, sir.
Okay. I'll just discuss a bit about
Sir,
this
from
non-ferrous
where
alloys
these
casting as well. We
are
can
these
end the
questions are
session.
from some previous assignments?
These are questions from previous assignments.
Okay, for practice, no, sir.
So we are instruct. Yes, yes, these are for practice. You can attempt the assignment as well. It will be easy now. I- So one topic is pending. I'll quickly go through it. Okay. I think is it visible? So this is about this non-ferrous alloys. So before that, we need to non-ferrous alloys. We need to worry about these various densities as well as melting points of alloys. Okay. So in one case we can get that one material is very dense, so it can settle down, and one material is like pure very less dense, so it can float on the top and there will be no mixing at all. And similarly the melting point, so one can melt easily and other cannot melt. So these are the difficulties, I can say. So the other is uniformity in chemical composition because of segregation. So this segregation occurs due to the rejection of this solid. So as I explained earlier, when the solidification is happening, this solid will have less solubility of the solute that we are adding. For example, aluminum, copper, if you take. So if the primary aluminum, well solidification aluminum will form alpha aluminum we call. So it will have less solubility of this copper, so it will segregate. So the copper will be removed sequentially, and the rest of the molten metal will get enriched with this copper concentration. So that is like called as a segregation. So we have so many types of segregation: macro scale and micro scale. Then this is one of the difficulty: non-metallic inclusions. Then loss by vaporization and absorption of gases, very important in aluminium because it is readily oxidizes and the temperature that we use in the furnace. So these are the some of the factors that we need to consider for non-ferrous alloys. For example, we have this alloying elements say lithium, magnesium, phosphorus, beryllium, silicon. These all float up and get oxidized quickly. So the problem with the oxidization is that so when they actually solidify completely, so we can clearly see the so this particle will be there, the lithium or magnesium, and on the surface we have this oxide layer which is brittle, so the properties will get lost because of that. So that is why we need to go for the master alloy. So master alloy is nothing but we completely melt whatever the metal we are using, for example aluminum. So we are directly pouring in the mold itself. There itself we will add this lithium, magnesium, everything. So that is the master alloy process. So example for this variation in density is copper and lead. Copper, I think it is having around some 8,000 kg per meter cube, whereas lead, I think around some 1200, below 2,000 kg per meter cube. So it has very good difference between the densities. And in terms of averages, zinc and phosphorus. So zinc and phosphorus evaporates at working temperature of copper alloys. Copper alloys working temperature is around 1000 degrees Celsius, whereas 1080 around, whereas zinc is at around some 420 degrees Celsius. So and phosphorus, I'm not sure. So by the time the copper melts, this zinc and phosphorus will get vaporized. So that is the reason we go for master alloy or addition just before pouring to prevent this. So this and the formation of dross are non-metallic inclusions. So these non-metallic inclusions, so these are the certain phases which are brittle in nature. So the same phenomena repeats when you are deforming it. So these are the first thing to break and form these cracks, and these serves as a crack initiations, and the rest of the property will be deteriorated with these phases. So casting defects during pouring and solidification. One is the aspiration. One of the main thing is the aspiration effect, which occurs due to improper design of the sprue or the gating system. So we need to ensure that at each and every point the pressure is more than atmospheric pressure. If there is negative pressure, there is always a chance to for the atmosphere some air get entrapped into the mold. Shrinkage occurs. This is unavoidable shrinkage, which is due to the density difference between the liquid and solid. So we'll have a very good difference between the liquid and solid densities. So we have to provide risers in order to compensate these shrinkages. So the rest is, I think, common defects. One is the surface defects and coarse grain structures. Alloys with large increases are usually susceptible to formation of coarse grain structures, grain refiners like aluminum and magnesium are used. So basically, these coarse grains are good because it has very good ductility, but at the same time, it has very less strength or yield strength. So that's why we need to refine these coarse grains. So that we can do with so many number of ways. One is by adding these grain refiners. We can add nucleating agents. We can superheat it and quench it immediately, or using chilling or vibrations. Vibration is what happens is it breaks the bigger nucleations so that the smaller grains will be formed later. Because if there is any big grain forming, if you break it, it will break into small pieces, and the small pieces itself act as a nucleating agents. So that is how we can refine the structure. First one is the copper and it alloys. Issues with the casting. So melting is one of the main defect for this copper. So it has a melting point of 1080 degrees Celsius, and it will not easily melt with basic induction furnace. We have to go for this bigger electric induction furnace, such as electric induction. Then we can go for this normal vacuum arc remelting, such types. So basically, we need good amount of copper. Basically, copper mainly used as electric conductor. So we have to maintain its purity. So we need to avoid these alloying elements because it affects the electrical conductivity. So we have a problem of oxide formation, such as cuprous oxides. Similarly, hydrogen forms porosity. So these are melted in the crucibles as fluxing and degassing are easier. Yeah, this is one of the main advantage in crucible furnaces, which are open to atmosphere. So it will absorb, but we can degas it. So these are the degassing agents that we are using: lithium, calcium, borate. So these degassing agents will be different for different alloys. For example, copper we are using lithium or calcium borate. Uh, for example, in aluminium, we'll have this halide flux cover, nothing but NaCl, KCl. This will be in certain ratios. When you add this, it will form a top layer on the that certain alloy, and it will prevent further oxidation. And it will also dissolve these phases, aluminum oxide, LiO3. Aluminum is very famous for its reactivity with the atmosphere. It will readily react with the atmosphere and form oxide layer, and it will dissolve hydrogen very nicely, and it will hydrogen porosity is the main defect in these aluminum castings in whatever the castings you do. So either you do high pressure die casting or normal gravity die casting, this porosity is there in every case. So basically, the methods are similar. We have to go for degassing operation to remove this hydrogen. So there are so many methods. Here we have a plunging method, or we can use tablets. So pure aluminum has very low strength. So we will have some of the alloying elements such as titanium, vanadium, in order to improve its grain, decrease its grain size, so that the properties are increasing. So now comes the magnesium. It is very famous for its low density, even lower than aluminum, but properties such as good castability, meshability, weldability. But the thing is, it catches. It is very volatile. It will catches fire very easily. So you cannot really do magnesium castings in open atmosphere. We should have a controlled argon controlled atmosphere in order to make these castings. So zirconium we use for grain refining this magnesium. Usually these are melted in steel kettles, require protection against oxidation. So this is the main thing. Exposed magnesium bath is protected by sprinkling sulfur powder. So this sulfur powder will reduce this that volatile nature of magnesium. So basically we are going to use with die casting. because it may react with the silicon dioxide, so molding sand mixed with sulfur and boric acid used. So basically, these are magnesium, aluminum. These are basically used in die casting uh, because of low temperature. Magnesium, aluminum we have around 600, whereas magnesium we have around 4 to 500, between 4 to 500 degrees Celsius. Yeah, that is about this non-ferrous castings. We discussed about magnesium, aluminum, which are copper. These are the main three non-ferrous castings that we use. Any doubt in these?
Sir, hydrogen porosity
Yeah.
in copper and aluminium is similar type, because they are
Uh,
creating a problem. No?
I didn't get your question.
Sir, like we are having the pinholes, na, you told in previously.
Yes, yes, yes.
So copper, it is creating the same problem, hydrogen.
Uh, we typically we will not see pinholes. Rather, we will see nice spherical shape holes inside the casting because these are low temperatures, so it will it will solidify very fast
Okay, sir.
compared to the steel castings which are having good solidification freezing range. It will have very less freezing range, so basically they will be trapped inside the mold.
Right, sir.
In some cases, we can also see pinholes, but generally, these hydrogen porosity is being seen inside the castings.
Right, sir.
We identify them by this circularity. It will be nice spherical shape.
Right, sir. Sir, how degassing is done?
So this is very simple. Degassing. So we simple method is we will have a tablets of these degassing agents. We'll just mix that with the molten metal, and we'll just mix it well. So this degassing agent will react with this molten metal, and if there is any oxygen, nitrogen present, it will form some slag, and
Hanji.
later we will remove that slag.
And tablets material, sir?
So this, we have given here.
Yes. But please.
So in this melt is dioxide with lithium or calcium boride. Okay, available in sealed copper tubes. This is one. So it varies with different alloys. In case of aluminum,
Hmm. Flux
I
cover.
think this, yeah, maybe this halide flux cover. But we'll have some. There are proprietary. We don't know exact the combination of those.
Yes, sir.
Yeah.
So do we have some videos or of casting of these different materials like magnesium, aluminium, copper, cast iron, and steel? Different
Yeah.
used for different
I
materials.
think I think it will be available. You can just have a look. I think they are available. So aluminum, I am sure they are available. You have to see magnesium and copper.
Yes, like the process we are discussing, sir, how they like remove the like hydrogen problem and this degassing and fluxing, how they do that. That's all we can see through the video.
Uh, I think generally they won't show you these things. Maybe they are
Okay,
proprietary, so they won't show you. But
right.
if there are some small castings, you can see. They can provide you.
Okay, sir.
Yeah. Yeah. Thanks for attending. We'll meet in the next session.
Okay, sir. There will be one more session.
Yeah. So there are total 8 sessions.
Okay,
So I
sir.
think next session will be covering the last class. Then after there will be one session in which we'll cover entire syllabus, just revision kind of.
Okay, sir. Fine, fine. Sir, actually, I want some
Okay.
numerical problems, solutions
Okay.
like gating ratio, riser design initially, no, sir, freezing ratio,
Yes. 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 Yeah.
and
Definitely.
Can we have, sir, some examples, or can you give some reference or books which I can open and see
Uh,
these
so,
problems?
so there is one book called Material Science by Ghosh and Malik.
Okay, sir.
So you can just practice those. It's very good book.
Material Science by Ghosh and Malik.
Ghosh and Malik.
Yes, sir. Actually,
I'll
sir, I
just
want.
send you a link. Uh, so I have just sent you a link. You can just check that is the book. So you can
Okay,
practice from that.
right, sir, right. Sir,
Okay.
actually, one more problem.
Yeah, yeah.
Actually, I want to understand the C curves.
Cooling curves.
Yes, sir. In which there is some
Okay.
formation of perlite, then bainite, then ferrite,
Okay. Okay.
and actually the heat treatment, basically.
Okay. Temperature time TTT curves.
Yes, sir.
Okay. I think the topic is also covered in that book. You can just have a look. It is very simple.
Right, sir.
So if you have that chart in your mind, you can easily figure it out. If you cool it faster, you will get this Martensite transformation. You cool slowly, you will have this perlite transformation or ferrite. So that you just have a look on the chart. You will
Right, sir.
get to know.
Sir, fine.
Okay then. Can I will
Thank,
close the session. We'll meet in the next session. Okay.
thank you, sir. Thank you, sir.
Thanks. Bye.